Good evening. It's a rather rainy Monday evening here in Norwich, but what a better opportunity to do a bit of maths, eh? What we're going to look at today is do a bit of Mechanics 1 revision, and in my opinion, the trickiest part of mechanics. Um, it's involving this equation here, this very important fundamental equation, F equals ma. Now, I've got four very common situations which effectively in the exam these will be the different kind of situations which occur when we're dealing with questions with F equals ma. Now the important thing to realize this is acceleration. Acceleration means that the object is moving. The object is not at rest. It is not in equilibrium. If things were in equilibrium, all of the forces would add up to zero. Now, Newton's second law and his, one of the key things of Newton's laws of motion is that when the forces aren't equal to zero, or when the object is accelerating, this equation comes into the fold. Okay, the forces no longer add up to zero; they add up to the mass multiplied by the acceleration. Now, notice I'll put a line under acceleration because I should also put it under force as well, because these are vector quantities, as we'll see in one of the examples here. Now we're going to start off with a pretty basic one. We're going to start off with this one here. Okay, let's just draw a circle around that. We're going to start off with this one here. Now here we've got an object. It is accelerating at 4 meters per second in this direction, so going from left to right, so we may as well make that our positive direction. Okay, and we want to find out this resistive force. Okay, this object here, don't know what it is. It could be a car, it could be a trailer, whatever. We know it's traveling at 4 meters per second. It's got a forward driving force of 50 newtons and a resistance to motion of F newtons. Okay, so very simply, this one we're just going to use F equals ma straight off. Okay, F equals ma. Now in this one, after F equals ma, we need to calculate that the net force which this object experiences. Okay, so to do that, it's quite simple. For this one, because it's traveling in one dimension, really, it's either going to go right or left. Okay, the net force here is going to be 50 minus F because it's traveling in this direction. If it was traveling in this direction, okay, it would be then F minus 50 if it was accelerating in the other direction. But here, because we've got acceleration going from left to right and it's positive acceleration, the net force is going to be 50 minus F. Okay, and that's going to be equal to the mass times the acceleration. Now in this case it's 7 multiplied by 4. Okay, a nice easy one there, which means that if I finish that calculation off, it doesn't take a rocket scientist to realize that F is equal to 22 newtons. Okay, because 7 times 4 is 28, so 50 minus 22 is 28. So there we have it. F is actually equal to 20 newtons. Nice, simple example there to start off with. What we're going to look at now is we're going to go around this way. Okay. Now again, F is going to be equal to ma here. The reason why it's F equals to ma here, again, we've got acceleration. Now here we've got two objects. So we've got a 7 kilogram weight and a 3 kilogram weight being held with a light inextensible string over a smooth pulley. Now the fact that that pulley is smooth means that the tensions in these strings are the same. Okay, so first of all I'm going to add some forces. We've got the tensions in the string there, which we're trying to find out, and we've got the acceleration, which we're trying to find out. I didn't want to do that, so if I control Z with that, I want an arrow here. So there's going to be force due to gravity for both these objects. The force due to gravity for this one is going to be 7g, and for this one it's going to be 3g. Okay, so I've added the forces on 3g and 7g. Now we're going to got two objects here traveling in different directions. Okay, because just change the colour as well. Let's go there. Right, that is really irritating, but there we go. This object here is going to be accelerating that way. This object gets accelerating that way. Okay. This object, the 7 kilogram, is accelerating downwards. Okay, so we're going to get two equations to solve simultaneously. So for this 7 kilogram object, because it's going down this way, the acceleration is going down this way, the net force is going to be 7g minus t. Okay, 7g minus t because it's traveling down that way. And that's equal to ma. The mass is 7, the acceleration is a, we don't know what the acceleration is, so that's equal to 7a. The other equation, now this object is moving upwards, so the net force now is going to be the other way around, t minus 3g, and that's going to be equal to 3a, because the acceleration is the same, the system is, the acceleration is the same going upwards, but this time the mass is 3 kilograms, okay? So, we have got these pair of simultaneous equations to solve. Now, at first thoughts, you may think this looks pretty nasty, but actually it's not too bad, because if we add these equations up, the minus t and the plus t will cancel. So we end up with 7g minus 3g, which is nearly said it there, 4g, and that's going to be equal to 7a plus 3a, so that's equal to 10a. Okay, and eventually we can get that a is equal to 4g divided by 10. Now, if we make g equal to 10, that just cancels it all out a lot nicer. So the acceleration here is equal to 4, which means that from this equation, so let's say let g equal 9.10. Okay, usually in the question it's 9.8. I'm just saving myself the task of getting a calculator out. Now, if we substitute a is 4 back into one of these equations, we'll figure out the acceleration. So if a is 4, let's do it into the top one. Okay, so we get 7 lots of g minus t is equal to 7 lots of 4, because we know the acceleration is 4. So in that, what happens there is that 7t is equal to 7 times g, which we know is 70, because we're making g is equal to 10, minus 28, which is equal to 42 newtons. Okay, so a nice use of simultaneous equations there in a question. First of all, set up, so just to recap, first of all, set up the equations for each object. Okay, they're going to be different way round for t, because one of them's traveling up, one of them's traveling down, and then solve them simultaneously. In this case, the easiest one was to add them up, and then just use your usual core, well, GCSE methods to solve that. Okay, there will always be two unknowns in these kind of problems. Acceleration is one of them, tension is the other. You cannot work out the acceleration nor the tension without having two equations. That's a fundamental thing. You know, the number of different unknowns we have in a problem means that we have to have that number of equations. Here we had two unknowns, a and t, and we had to have two equations. Okay, and that's a very useful philosophy to have when you're solving these mechanics problems. Okay, I'm going to get rid of that now. I'm going to have a look at this problem here. Now, what we've got here is effectively a car 20, or some car 20 kilograms, obviously a bit ridiculous, a little toy car, pulling a trailer 10 kilograms. Okay, there's a driving force from the car of 60 newtons, and it experiences resistance of 10 newtons. This could be due to air resistance, or it could be to the surface of the contact of the car on the road. Either way, we're not worried in the MEI syllabus about a model for friction. We just accept that will be friction. The trailer just experienced no driving force on the trailer. It experienced a frictional force, and the coupling in between them, the rod in between them, light, inextensible, so we don't have to worry about mass or Hooke's law, but there's a tension there. Okay, and by Newton's third law, those tensions will be the same. Okay, and let's make sure we know what we're talking about here. This force is the force experienced by the car. Okay, change colours here. This force didn't change the colours at all. This force is the force experienced by the trailer. Okay. Now, two unknowns here. Two unknowns here again, and we're thinking to ourselves, how on earth are we going to do that? Two unknowns, can't get it off. Really annoying. Two unknowns, how are we going to do that? Well, this is where, in this problem, we treated each object separately. Now here, we've got a problem, because F, the frictional force, which we want to find acting on that object, only affects that object. Or, well, at the minute, it only affects if it only affects that object. And we've also got T. We've got one equation which we can have T minus F is going to be the net force for this object because it's traveling in that direction. Now for this one, we're going to have 60 minus 10 minus T, and that's going to be traveling in that direction. Now, we could do this by doing them separately, but I think a better way to do this, in fact, we can't do it separately, sorry. The only way to do this in problems similar to this, we'll get it straight in the end, is to sort of treat the system as a whole, first of all, and then treat one of the objects separately. So what we're going to do is we're going to treat the object as a whole. Now, let's just get rid of that for a second. Let's move it up here so we can see what we're doing. Now, travel in that direction. So the net force for the whole object, let's treat this as 1, is going to be 60 minus 10. 60 minus 10, so there's 60 minus 10. And we're going to have a minus t, because we're taking away a t. But then we're adding a t as well. Now, that's really nice, because that means the minus t plus t is just going to cancel out. Okay, so we eliminate that variable from this equation, which is lovely, because then we can work out f, because we need to subtract f, and we know that's equal to the mass. Now, the total mass, because we're treating the system as a whole, is 30 times the acceleration, which is 4. Okay, 30 times 4. Now, that means that we're going to have, eventually, 50 minus f is equal to 120. Which means that f is equal to 50 minus 120 minus 70. We've got a negative answer there, which, well, basically it's saying that the frictional force is the other way. It doesn't matter too much. We shouldn't really get a negative answer there. I think it's the numbers which I've chosen which have made that possible. But the method is sound, okay? Frictional force minus 70. So now let's find the tension in this coupling. Now we only have to treat one of the objects now. Let's just deal with one of the objects. And it makes sense because we've got an F there. It makes sense to use this one, okay? Let's have a look at the car. Now again, our force, net force is going to be 60 minus 10, so that's 50. I'm just going to go straight into that. 50 minus T, because we've got that T there, 50 minus t, and that's going to be equal to 20 times 4, which is 80. Okay, and again, we're going to get t negative, and t is going to be minus 30 newtons. Now, this is possible. The thrust, the tension there could be negative. Now, what that actually means is that we've got the arrows wrong. Shouldn't have been that way. The forces for these should have been pointing in the opposite direction, because we got them as negative. Now, what that means is the force which that object experiences is being pulled, it's experiencing force that way, which means the rod is being pushed inwards by Newton's third law, okay? The force which this object feels due to the rod is pushing it inwards. So the force that the rod feels from the object is pushing it outwards. And similarly for the other one, the force the rod feels from the trailer is going to be inwards. Now that means that this object isn't actually in tension, it's actually in what we call compression, or thrust is another name for doing it. The rod is being pushed together, it's being compressed together. So, that's a problem involving truck and trailers. I'll delete all of that there. The numbers are a bit weird there, I do apologise. But the method is sound, Now, this is with a fiddly one. Here we're going to have to treat them as vectors. Here we've got an object on an inclined slope, 2 dimensions. We're going to have to treat it as vectors. We've got a resistance to motion of 10, a driving force of 13, a normal reaction which we need to find, and it's accelerating down the slope at 2 meters per second. Now we have to add a force in here. We have to add gravity. Okay, so there's our gravity, and that has a magnitude of 7g. Okay. Now we need to split this vector into components parallel to the slope and perpendicular to the slope. So first of all, this one's perpendicular, and here we have it parallel. Okay. Now we know that that angle via parallel line theory is going to be equal to alpha. Now I'm not too sure we're going to have an alpha. Yes, we do. Lovely old job. That angle there is alpha. There we go. Move that up. That angle there is alpha, which means that I'm going to use A for this because otherwise that one there is going to be 7g sine A. And this force here, this part here, is going to be 7g cos A. Okay, I'm going to use A is basically alpha there because I can't be bothered to sort that out each time. Right, let's get these equations as vectors now. I'm going to have to write here, so apologies for the handwriting. We need to define our I and J. It makes sense to make our J perpendicular to the slope and our I parallel to the slope. And now we need to write these as vectors. Okay, so R is going to be 0R. This one's going to be 13, 0, because these are all positive forces. That is a shocking 13, but you can understand how difficult this is with the mouse pad. This one here is going to be minus 10, 0. That's shocking brackets. And right, oh, I'm really not looking forward to this. All right, here we go. I'm just going to use that. Now, horizontally, it's 7g sine A, and the arrow's going in the positive direction because it's going down the slope, which we've said is our positive direction. So 7g cos A. And the other one is going to be minus 7g sine A. Okay, so let's just get that. So there's our vector, our fourth vector. So it's minus because this bit here is going down. Okay, and I've got them completely the wrong way. Do apologize for that. This is a common mistake you can make. It should actually be the other way around. That should be a sine. We'll talk about that in a second, and that should be a cos. You spotted that mistake. Well done. It shows that you're understanding. Yeah, it should be a sine there because that side is opposite the angle. This side is adjacent to it. Okay, and I actually labelled them correctly there. That was a very silly mistake of mine. So I'm going to move this down because I need some more space to do the calculations here. So I'm going to add all these vectors up. We'll get 13, 0. So there's our first vector. Oh, this is so annoying. I hate this. I had one of those touchscreen jobbies. I hate technology, so that is no going to happen. Minus 10, 0. Zero R. Whoa, uber brackets. R, lovely old job, and plus. Right, I'm just going to copy and paste that because I can. That's just going to be irritating to draw all the time. Now, this is equal. This is the resultant force, and it's equal to ma. Now, the acceleration is only in the I direction. Okay, so ma is only going to be in the I direction. So 7 is the mass. Acceleration is 2. So that's going to be equal to 14. So 7 times 2, which of course is equal to 14. So I'll just write 14 there. Okay. Now there's no acceleration in this perpendicular direction. This is going to be equal to 0. Now, we've got two equations here. We have the top equation there, and we have, and I'm determined to sort this, save tool properties, determined. Yay, it's green. We have the yellow equation and the green equation, and we can use these to solve these problems. We need to find A and R. Now the top one just involves A, so it makes sense to use that one to work out A. Now we have 13 minus 10 plus 7g sine alpha A is equal to 14. Now 13 minus 10 is 3, so 7g sine A has to be equal to, yeah, don't know what happened there. I'd have been well annoyed if that had deleted everything. So we have 7g sine A is going to be equal to, well, 14 plus 10 minus 13, which is 11. Okay, which now gives us a nice little equation, simple little trig equation to solve. From there, we know that sine A is equal to 11 over 7g. Now, using a calculator, I'll get rid of that. That really annoys me, that. Using a calculator, sine A is going to be equal to, right, I think I've got a cheeky little calculator up there. Go to there, calculator, add that onto there somewhere. Lovely old job, done. Ah, it's just a normal one. That's annoying. Right, 11 divided by. In fact, let's just go straight into A, because I think we'll lose accuracy if we start rounding up. So let's put the calculator. I was hoping it would be some next level one. Anyway, let's do 11 divided by 7 times 9.8. So I'll have to divide that by 9.8 as well. So there's 0.016. Now let's arc sine that. So inverse sine, we get 9.23. I'm going to keep it as 9.2 degrees, because there's no way we're going to get that any more accurate if we were trying to measure it. So no idea where that degree symbol could be there. Degree C, definitely not degree C. Right, rather than waste your time trying to find that, I have no idea where that is. Make it an asterisk? No. Right, 9.2 degrees. Let's not get too wound up about that. Now, the green equation could be solved, because we know what A is now. We know that from here, we basically get that R is equal to 7g cos A. Okay, nice and simple there, because all of the other, they all add up to 0. There's no acceleration in that perpendicular way. So let's whack that straight into a calculator, and so 7 times 9.8, keeping G 9.8 this time because it can, times by, right, let's see if we can figure this out, because this isn't the best calculator. 9.2 cos, that looks all nice. That looks a bit of a small thing. I've checked I'm in degree mode. That seems fine. I didn't inverse that. Let's do it again. Such a numpty sometimes. 7 times 9.8. 68.6. I'm very surprised about that, because I'm going to do it the other way around. The calculators you've got will be able to do this straight away. A is 9.2. So if we do the cos of that, we get that. Yeah, that's better. Times by 7 times by 9.8. I don't know what happened there in the calculator. It looked too small, that number. 67.7 newtons. And there we have it. Okay, we found R and we found the angle. So that was an overview of 4 kind of standard situations which you could encounter in the exam when it comes to F equals MA. The maths isn't difficult. It's just solving the problem and knowing how to do to solve the problem. There's little tricks. Simultaneous equations for this one. Treating the system as a whole, treating the system as one when we have 2 connected bodies with a coupling there. Changing your I and J direction so that it's parallel and perpendicular to the slope. These little tricks where if you can master all of these, your mechanics becomes a lot easier to deal with. Good evening.